Welcome to Everything Explained in 5 Minutes, the podcast where complex ideas meet clear answers. Today, we're diving into a concept that sounds like science fiction, but is very real and very close to changing everything from medicine to cryptography to artificial intelligence. We're talking about quantum computing. Now, you might be thinking, I barely understand normal computers. What makes quantum ones so different? Well, that's exactly what we're going to break down in just 5 minutes. Let's go. Let's start with what you already know. Classical computers, like the one in your phone or laptop, process information using bits. A bit is either a 0 or a 1. Everything digital, from text to TikToks, is made of long sequences of these zeros and ones. But quantum computers don't use bits. They use qubits, short for quantum bits. And here's where things get wild. Unlike a regular bit, a qubit can be a 0, a 1, or both at the same time. This is thanks to a property called superposition. Imagine spinning a coin. While it's spinning, it's not heads or tails, it's a mix of both. A qubit works the same way, only it's governed by the rules of quantum physics, not gravity. Now take entanglement, another key idea. When two qubits are entangled, the state of one instantly affects the other, even if they're miles apart. Einstein famously called this spooky action at a distance. So why does this matter? Because when you put together a few entangled qubits, each capable of being in multiple states at once, a quantum computer can perform many calculations at the same time. A classical computer would need to check possibilities one by one. A quantum computer can explore thousands or millions simultaneously. Let's bring this into real-world impact. Microscope medicine. Quantum computers could simulate how molecules behave at the quantum level, something classical computers struggle with. This could unlock new drug discoveries faster. Locked with key cybersecurity. Today's encryption relies on math that would take classical computers thousands of years to crack. Quantum machines could, in theory, do it in hours. That's why post-quantum encryption is now a hot field. Globe showing Europe-Africa climate modeling, logistics, AI, all of these involve complex systems that could be solved more efficiently with quantum processing. But, and here's the key, we're not quite there yet. Quantum computers are still incredibly fragile. Qubits are sensitive to noise, temperature, even magnetic fields. Right now, maintaining a working quantum state for more than a few microseconds is a challenge. Companies like Google, IBM, and startups like Rigetti and IonQ are racing to fix this. In 2019, Google claimed quantum supremacy by showing a quantum computer could solve a problem a regular one couldn't, but it was more of a demo than a revolution. So where are we today? We're in the early days, kind of like the 1950s of classical computing. Machines are huge, expensive, and specialized, but the potential is enormous. Think of it like this. If classical computers are calculators, quantum computers could become laboratories. Will you be using one to stream Netflix anytime soon? No. But could they one day help design new materials, optimize supply chains, and solve problems no classical computer ever could? Absolutely. And now you know how they work. That's quantum computing explained.